Okay, so actually the other name for the lesson is this IV characteristics. And Ohm's law is in it, don't worry. So if you can write this down, please. I didn't send this to Connell yet. Or did I?
You should change your phone.
No, I'll just check my outbox. Okay, did you write that down? IV characteristics. Yeah, I did. Continue? Got that? Continue?
No.
Oh, come on.
Okay, you can continue. I read it.
Okay.
You have to after that.
IV.
I wrote over.
Thank you. Right. So, let's have a look at this very simple circuit below here. Very simple, but very important. So first thing I want you to do is to draw this circuit, and then we can explain why it's important. One sec. Please. OMG. I'm thinking that if you do have to do the exams before the break, it would only seem fair to make the coursework due after the break. So I don't really want you to submit your coursework in a week where you're supposed to be thinking about and doing study for your exam. So I'll just open up the Moodle link and you can submit it whenever, and I'll close it after the break.
Submit it fine.
Well, yeah.
This was supposed to be this week.
No, like next week. But you need to be thinking about your exams, if, you know, right before the break. Anyway, did you draw this?
Mm-hmm.
Yep. So, let's talk about what happens here with the variable resistor. So, I'll draw this too, it'll be easier. Now there's a couple of different ways you can draw it, it doesn't really matter. So in my picture I'll put the resistor at the bottom and I'll put the variable resistor here. Not that it matters. Or maybe I'll put it here. And I'll put my ammeter here. I'll put my voltmeter here. Do I need? Of course, yeah. And I should have a switch, shouldn't I? It's the same thing. You have the voltmeter on the resistor with the ammeter and the power and the variable resistor. I just did it upside down. Anyways, let's have a look here at what happens. If this is set to 0 ohms, then it means, and we'll call this voltage here, I'll just call it E, volts. Then the voltmeter, it should read E. And the reason for that is all of the voltage from the power supply is being used in this one resistor. The total is equal to just the one voltage. Now, if I increase this, if I could measure the voltage, which I don't, but if I could, this will start to increase here. So I'll call this V1 and I'll call this V2. But I can know that V1 plus V2, that should equal total, which we said is E at the beginning, because that's what the battery can provide. Now, this gives us the reason why we have the variable resistor here. The job of this variable resistor is actually to change the voltage on this one. So, as you increase this, V1, what should happen to the V2? Decrease. So you can increase this to make a decrease here in the voltage. So what will happen is the voltage V will change, and at the same time the current here will also change. So the I will change. So what we'll do is we'll plot those two on a graph, how the V and the I change. And this is the reason why this circuit is important, because it can give us the IV graph for this or for any resistor. And we'll see why this graph is important in a moment as well. So what I would like you just to add to this is just to make a note that the job of this is actually to change the voltage and the current. That's why this is on the circuit, the variable resistor. Do you understand what you need to write?
Why current is changing?
Because the V changes. Because if you think about the formula, VI-OR, the I equals the V over the OR. So if the V changes, the I changes too.
And the R changes.
The OR can change.
Because it's a relation.
Yeah, the OR can change. But how the OR change depends on the resistor. Some resistors the OR changes a little bit, and some resistors it changes a lot.
The total force is same, right?
Yeah, but the V in the formula is, we're just looking here. We're just looking at this. We're just looking at this V and this I and this OR. Yeah. Okay, did you make note of that? Yeah? No.
So in the variable resistor, we change the R to change the voltage on it.
Yeah. The only job of this guy is to cause changes here and result in changes here. So in a way, this is a cheap way to change the voltage. You can't actually get power supplies where you can change the voltage on the supply. You like just turn a dial, you can set the voltage. But of course, it's much easier to have a power supply with a fixed voltage, like a battery, and then use this variable resistor to change the voltage on this resistor here. So it's just a cost thing. Continue? Yeah? So, here is an example of some data that you could get. You have the voltage, and the voltage started off at 10, and then we increase the variable resistor. We see that the voltage decreases all the way down to 1. And what's happening to the current? It's also decreasing as the voltage decreases. Well, let's plot this data. So I want us all to make a plot where we put V here and I here. So if we can all plot this together, I need you to put this in your notes. I'll make a beautiful one here using a program. But I'll just give you a minute to draw this. Remember, I want V here, because that's what we're changing, and the I here. VI. Okay. Just draw this
Graph or table?
are you doing this on purpose? V I
Graph or table?
graph. Well, you should write the table too.
I.
I do it. Wow. I stopped focusing on your bread and which one's V? No, I want to make sure you know which one's V. Go, Dorothy. Got that wrong? Oh dear.
And it's the ugly one.
Ugly one is okay. Let's see, how ugly?
Ugly.
So ugly. What?
Hi.
Okay, let's have a look here. So, voltage in volts, current in amps, 10, and then 9, 8, 7, 6, 5, 4, 3, 2, and 1, yeah? Yeah. Right, let me make the graph here. Insert chart. And I'll need a scatter plot. And okay. IV curve. Fixed resistor, voltage or potential difference in volts, current in amps. Okay, so you all should have something that looks like this. Yep. Let me just shrink this down a little bit. Now, let's see what we... Okay, let me just get this out of the way. Right, what do we notice about this graph? What are some features about this graph that we notice? It's linear, isn't it? Yeah. We might like to know what the slope of this linear graph represents. So, if we think about this, we know that V equals I or rather we should say I equals 1 over or B. And on this axis we put V, that's like the X, and on this axis we put I, that's like the Y. So what would be the slope? What would be the gradient of this? 1 over R. Or is 1 over the slope. So we have a meaning of the slope of this graph here. So I think I might say, yeah, I'll get to that in a moment. But the slope is 1 over R is 1 over the slope. So this graph is very important in electricity. It's called the IV characteristics of a resistor. So if you have a resistor, it's very important to know what the graph, this IV graph looks like. Because it tells us something about the behavior of the resistor. So what is the graph? The graph is simply a plot of the current running through it against the voltage around it, when a power source provides a change in voltage. So in my picture here, the way we were able to change the voltage was by using a variable resistor. It's the easiest way to change it. So that's the IV characteristic graph. So that's why I said the circuit is important, because this simple circuit is the circuit you use to make this. Now this is important for 3 reasons. It's important in physics because we like to know its behavior. It's also important in the exam because they would sometimes ask you to make this circuit or to do a question with this circuit. And it's also important for your experiments because one of the experiments you will do next semester is this experiment of making this graph for a resistor. So it's very, very important graph. If you could write the definition down, you don't have to write exactly this, but you should at least write IV characteristic is a whatever graph you want to call it. But this is an important word here, IV characteristic. So you should write something down, please. Connell said anything? No, it's not Connell. You wrote something? Okay. What are you up to? Did you open the packet sideways? Interesting. I've never seen anyone do this before. Why? Okay. Okay. Now, what is Ohm's law here? Some people may know Ohm's law from high school.
No.
Say again?
Voltage is directly proportional.
Nearly. More or less that. So Ohm's law is a statement about the relationship of current and voltage for a resistor. Yeah. So Ohm's law states that for some, now before I continue, the bad thing about Ohm's law is it's not really a law because it doesn't work for every resistor. So for some materials at a low voltage and a low current and a constant temperature, the IV characteristic graph will be linear, which is the same thing as what you were saying, that the voltage and the current will be proportional. But it's only true for some materials, and it's only true at low voltage and low current. So it's not really a super useful law, because it's not even a law that's true everywhere. It's only sometimes true. But this is technically Ohm's law. So in the exam, you can't say voltage is proportional to current. It wouldn't be enough to say that. So for the exam, you actually do need more than that. So you should write all of this down, please. All of it, please.
Okay, I remember.
If you understand it, you can remember it. Got that? Continue? No, I see people writing some. You saw that our Irish leader met Trump today. Huh? Because tomorrow is St. Patrick's Day, so every year the Irish leader goes to America to meet the president.
Why doesn't he come here?
Huh?
Why doesn't he come here?
He might come here in the future, but it's normal for the Irish leader to visit the American president. Yeah. This is usually a tradition of maybe about 50 years. You didn't see this on the news? You saw this? Continue. Are people going to the parade tomorrow? Huh? Anywhere in the city centre, O'Connell Street. Yeah. Well, yeah, it's like National Day.
There by like 9.
9 would be good, yeah. Well, it depends if you want a really good spot.
Where's a really good spot?
The gate?
O'Connell.
Huh?
Is the gate?
No.
There was a good spot.
It's a good spot.
Fire.
Yeah. I'd say anywhere on O'Connell Street near the bridge.
Are you going near the bridge?
No, because my hometown has this. Most towns have their small local parade.
Oh, you're not living in Dublin?
Oh no. I'm quite far away. Quite far away.
So you're going back to your hometown?
1.5 hours.
Yeah.
Huh?
You're going back to your hometown?
Every day. I live quite far out from Dublin. Quite far out. Do you have this? Yeah. This is not always true. You see, I was just saying this law isn't even always true. So if it is true, we call the resistor an ohmic resistor. Otherwise we say it's not ohmic. So it's kind of a silly law. We say if it's true, we say it's ohmic. If it's not true, we say it's not ohmic. Sometimes it's true, sometimes it's false. Okay. So do you need this word ohmic? When it's true, we call it an ohmic resistor. Ohmic, yeah. Huh? What's so funny? No. Something, I bet now ohmic must be some dirty Arabic word, is it? No? No, what then? What's so funny?
Ohmic means that your mother.
Yeah?
Yes,
That's it?
Yeah.
Oh, that's not funny.
Why you feel so dirty?
It's just the way she was laughing. I thought it was something really dirty that she said in Arabic. Like you called someone, you're such an ohmic. Right, do you have this? Yeah. And we already looked at what the slope represents. So I think you wrote this down, that the slope is 1 over r. Yeah? You got that? I think you should have that written down already. Yeah, okay. Good, okay, continue. So here's an example. We'll do this one together. So you would like to know the IV characteristic curve of a filament lamp. Now, does anyone know what a filament lamp is? Yeah. So where would you see this nowadays? Because you don't really see them in the lights on the ceiling, because they're usually LEDs. They're usually energy efficient lights. Lamp is usually where you see this filament lamp. Yeah, like a study lamp. You know, the ones that are on study desks, these lamps. And you notice that these get really, really hot. Really, really hot. So, we don't need to do part A, because we've drawn the circuit already. So let's go straight into part B, which is to make the graph. Now, I'll make the graph and you can just draw it roughly. But what I wouldn't need you to do is just write down this table, the data. Okay, do you have that table? Yeah? So, all I need to do, because I have my Excel program open, is just change the values in my table. Yeah, continue? Yeah. Do you need to look at something here? No? Can you tell me what the first voltage was? Oh, it's the same, 10 to 1. Okay, so it's 14, 13.5, 10, 9, 10, 8, 6, 4, 2? Okay. So, this graph, maybe if I extend it a little bit, it will look a bit clearer. Oh, no, I think that's clear enough. Would you say this graph is linear? No, it's not linear. It's not linear. So what's happening to this graph? What's happening to the slope? Is the slope getting bigger or smaller? Yeah, it's getting smaller. So if you were to imagine the graph like this, if you look at the slope here, and if you look at the slope here, this one from here to here, the m is decreasing. So what is happening to the r? Increasing. So this means with the filament lamp, as you increase the voltage, you get more resistance. It's not a constant graph. Let's calculate the resistance. Now the problem is the resistance is not constant. It's changing. So because the resistance is changing, what I want you to do in this question is calculate the resistance at each point. So R in ohms. But this isn't that hard because what's the formula for R?
V over I.
Isn't it? Yeah, V over I. So V over I. Oops. So look what's happening. As I increase the voltage, I get the current to increase, and I also get the resistance to increase as well. What the heck happened? I didn't touch any. Oh, okay. I get the resistance to increase as well. Yeah. So, would we say this material is ohmic? No. And what's the smallest and largest resistance? The smallest resistance is when the voltage is 5 or less, we get half an ohm. But then when the voltage is increased to 10, we get the largest resistance, which is 0.71 ohms.
What's the point to change the slope?
Yeah, what we notice with a lot of materials is that it looks like it's ohmic, but then at a certain point it stops being ohmic. It's a bit like, do you remember we had the elastic limit? It looks like a straight line, but then at some point, for some reason, it's no longer linear. And the reason is because of the type of material it is. So something is happening in the material. Now I think what's happening is it's getting hotter and hotter, and at some point it gets so hot that it affects the resistance. I think this is what's happening. Because I do know if you increase the current in a material, you produce more heat. So I think this is the main cause. So I think what happens is for low temperatures, the heat is able to disappear quickly into the air. But as you increase it, maybe the heat gets trapped, and this is what causes the increased resistance. So I do need you to draw this graph, and I want to make sure the graph that you draw so that it curves off at the top, okay?
Then this part is ohmic, this is not ohmic, and total not ohmic.
Interesting. We usually use the word ohmic for when the whole graph is linear. So what we could say is it behaves like it's ohmic for this part. But we can't really say it's ohmic because ohmic is a word we use for the whole graph. Did you draw this?
The whole graph is ohmic, but then you say as it increases it curves. That means like all of them is.
I suppose you could say, like, the problem with the definition of Ohm's law is I said at low temperatures. So, like, what do I mean by at low temperature? You know, so the thing about Ohm's law is it's not really a law like how Newton's law is a law, or how Snell's law, or whatever. It's more like just a general description rather than an actual formal law, you know. But you're right, if you increase the temperature and the voltage high enough, then eventually it won't be linear, and this is true for everything. Because, I mean, if you increase it enough, it'll probably explode. Then you get zero resistance. Or infinite resistance, perhaps. Okay, continue. Yeah. Next. So, what about if we put the current backwards? So, for example, let me show you my resistor again. Here's my little resistor. If I turn this resistor around, do you think that would make any difference? Well, it shouldn't make any difference. So, if you change the direction of the current, the only thing that should happen is on the voltmeter and the ammeter, you get minus and minus, but you should get the same number. The minus just shows you that the direction has changed, right? And this is true for most things, but it's not actually always true. So, for a simple ohmic resistor or for a filament lamp, the graphs can be extended backwards. Let me sketch that for you. So, for example, here is an ohmic material. This is V, and this is I. And in blue here, this is ohmic. But if I turn it around, get the negative voltage and negative current if it's going backwards, then you won't be surprised if I just draw the same graph except all the values are negative. Maybe that's not surprising.
What is nasty one?
It just means the direction is the other way. That's all. What is going on here? Is it falling out the back? Come on, you can do it. There we go. Now, what was I saying? Oh yeah, so it's the same except just minus values for the V and the I. Now, the filament lamp, we notice with this graph, let me just turn my key back on, my pad. Okay, so as I was saying, I'll do this one in red. What is going on with my TV? Is it a TV or is it a laptop problem? That is a key question now.
You have more
I have. Yeah, that's true. I can. I could investigate. Oh, come on. What the heck? Gosh, you should be helping me. Where's the support?
Go, Steven.
Thanks.
You engineer teacher.
I'm not a good engineering teacher. Alright, we're back. Right. Now quickly, before it disconnects again. So, the ohmic material we know will be straight and then flattens out, the filament lamp. And so likewise, you get the idea, it'll be the same, but on the other side as well. So this is for the lamp.
But you said the lamp is not ohmic, right?
Oh yeah, so I'm doing two on the same graph, say, drawing it again. So if I draw the resistance, the IV for the ohmic material, it's straight. For the lamp, it will be straight, but then it curves as it goes up the top. And we said when it curves and flattens out, what's happening to the resistance? It's increasing. Yeah. Remember we said that because what's happening to the slope? Decreasing, so the resistance is increasing. And again, you're not surprised that it's the same graph down here. It's just backwards. Yeah. But I think I have one last situation here. There is something strange if you use an LED. You know an LED? Like like most lights are LEDs nowadays. If you draw the graph for the LED, you get this very strange situation. This is a very, very strange graph for the LED. So what happens when I increase the voltage? What happens to the resistance? Decreases. So as the LED has more voltage, you actually get less resistance when the current is forward. And then even stranger, if you put the current in backwards to the LED, what happens here? You get a large or small resistance?
Large.
Very large, because the slope is very small. And then you get very large resistance, and then all of a sudden you have what's called a breakdown. And then all of a sudden the resistance decreases. So the LED, if you put the current forwards, you get little resistance, and if you put more current and more voltage, you actually get less resistance. But if you try to put the current in backwards, you get a very, very large resistance. Very large. And if you have enough voltage and current backwards, then all of a sudden it's like it breaks and no resistance then, or little resistance. So you have these breakdown point. This is the forward current, and you see this is called an avalanche current. Do you know this word avalanche? Is when all the snow falls down the mountain. So it's called an avalanche because all of a sudden all the current just begins to move. So LEDs are very interesting because they only like the current to go one way, and the more current and voltage they get, the less resistance they offer. In the exam, you need to know these three graphs. You need to know the ohmic, the lamp, and the LED, because they could ask you to sketch one of them. The hardest one to remember is the LED because it's so strange. So can you draw the three graphs? The lamp? Well, we did the ohmic, we did the lamp, so now you need the LED.
During exam, do you need to label?
Usually in the exam, for this graph, for example,
Yes.
they would definitely need voltage and current on the X and Y, obviously. And I think they would like as a minimum they would like you to label this point because it's an important point. It's where it breakdown. But a lot of these words are just for me to explain to you. So for example, obviously this is forward because it's positive, and obviously this is reverse because it's negative. You don't need to write those words in the exam because you know that from this and this being positive and negative. But you should write a breakdown at least. Yeah. Oh, and also because it's an LED, the voltage is the current and voltage is measured in millivolts and milliamps because it's an LED. It's quite small. What's wrong? No? Have you seen this graph before? No. It's interesting. The LED prefers one direction. Not bad.
Do we have to answer today?
You didn't reply to my text, if you can believe that.
Yes.
You can believe that?
You said it didn't matter.
Well,
No, wait,
true.
But you do they talk to you about the exam, right?
We did have a conversation about the exam.
So you
A little bit.
but you don't ask.
No. The exam, to move it would also mean moving the exam date in the DIFC Cork school. You know, we have another school in Cork. So it would mean they would have to change their date as well.
Why?
Because they're using the same exam. So,
And
complications.
Did they finish the required?
They did because they started in October. So you started in January, they started in October. So they are well finished.
Why they start so much earlier than me?
And
Why did you start in January and not September?
Like they have exams.
Oh, so maybe they have similar reasons. I don't know. Yeah?
Why didn't they start September then? They
Maybe
don't
they
have
had
to-
exams too, I don't know.
They don't have to do intakes, right?
They do not. No. No, they just opened recently, so just wanted to say. Did you draw this? Yeah? Okay. So that's all. I haven't decided if I want to do assessment support or physics class later, because my problem is I'm not sure if we can move the exam or not. If we can't move the exam, then I would rather do a physics class. If we can move the exam, then I want to do assessment support. But it doesn't matter, because we can still have assessment support next week. But I just don't know what would be better, assessment support or exam or physics class.
Same word.
Yeah, same. So I don't know what to do. Do any of you have a preference? Physics class versus assessment support at 4 o'clock. Any preference? Physics class preferred? Anyone else? Huh? I don't understand what you're saying. What are you saying?
When is our exam?
I don't know.
Gas.
Assessment support.
We brought our laptop.
You brought your laptop.
I didn't.
Oh, now the truth comes out. Okay, well, since you went to the trouble of bringing your laptop, we should do that, okay? Right, I didn't get a message from Connell, so you should just head to your chemistry class.
Huh?
Oh, it's in here? Okay.